That more or less says that every atom wants to make full octet of valence electrons and become happy. And based on this observation, you just build all possible molecules. But we know that this is not very good theory, so finally we learned something what was called valence bond theory. And in the valence bond theory, you are using atomic orbitals to build molecular orbitals. And you explain the shape of the molecule and the bonding in the molecule via the linear combinations of atomic orbitals. Today we learn something what is between. It's called VSEPR theory. Which is a nice way of taking the observation from valence bond theory and making them kind of easy. We'll see in a moment. What is the name meaning? The name means valence shell, electron pair, repulsion. From the first letters of these 5 words, you make the VSEPR name. In the VSEPR, there are 4 rules to explain the shape of the molecules. Rule number 1. Regions of high electron concentration and we know that the regions of high electron bonds or these are electron pairs. The regions of high electron concentration repel each other. Which means they want to stay, maybe if you don't know the word repel, repel means stay, push each other in the other direction. Attract, repel. Repel each other, they want to stay far from each other. This is the rule number 1. What does it mean? It means that you have atom A, and the atom A has 3 bonds
two lone pairs, then you can expect that one bond will be here, one bond will be here, and probably the lone pairs will be showing something like this. It's probably the best special arrangement of there are three bonds. It's easier to write it here. Bonds, three lone pairs. So that's probably the special arrangement of the lone pairs and atoms, bonds for this atom. You already recognize this picture. That's what we were drawing yesterday for hours. So you know that depending on the number of bonds and depending on the number of lone pairs, you can do different pictures of the algorithm. So this is exactly the pictures that we were showing yesterday are coming from the first rule of the DSEPR theory. Second rule, no difference between single, double, triple
bonds.
This is the rule that I like most. Because we have a molecule, for example, CO, O, 2 minus, that you should write double bond, single bond, and single bond. But the experiment is telling you that really the molecule looks like that. If you 120 degrees and the same distance here, then you see clearly that there is no double bond in this molecule, and there are no single bonds, because all the bonds are the same.
This is exactly the rule second, saying that there is no difference in geometry between the single, double, triple bonds. It means all bonds have the same length. For all bonds. There is rule number 3. When a molecule has more than one central atom, you apply rules 1 and 2 to each of them. This rule needs some explanation, and maybe I do this explanation. Let's take some more complicated molecule, which of course not necessarily is complicated. For example, C2H6. We have C2H6. We know that the bonding would look something like that. C, C, H, 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 H. Some mistake? Now we want to use the rules of SEP. We see there is no lone pairs on carbons, but each carbon has 4 bonds. But we know that each of the carbon would have the sp3 hybridization. So we can try to write the structure. It would be C connected to C. Now one of the bond would go here, the other would go like here. Now, there is a problem with the other side. I'm not sure if you see the problem, but I can draw 2 possible structures. I prepare for both of them. So one of them would have the hydrogen in the plane here, another one would have the hydrogen in the plane here. A, B. Now you see that all of them are following the SEP rule as so far. First, regions of high electron concentration, means bonds, are as far from each other as possible. Second, there is no difference between single and triple. This is boring rule because there are only single rules, single bonds. And when molecule has more than one central atom, this is exactly the situation. One central atom with sp3 and one central atom with sp3. We just applied the first rule twice. But now we got a problem because both of these structures are correct according to the rules, but now they look kind of different. Which of them is correct? The correct answer is that we can calculate energy for both of these structures and we can make a plot of energy when you think about rotation about this bond. Okay? When this bond is rotating, you can imagine all possible ways. How that energy plot looks like. Let's plot it. That would be the energy. And here would be the angle. Let's call it phi. Here the angle would be 0. And here would be pi. And here would be 2 pi. Probably in the high school you preferred using the 180 degrees instead of pi and 360 degrees instead of 2 pi, but probably in the university you will be always using pi and 2 pi, so get used to it. So how does it look like? When I say 0, I mean that these 2 hydrogens are on the same side. So this is the 0 angle. And this one is the pi structure when they are at the 180 degrees rotated. Okay, so now I can plot the energy. Turns out that the energy of 0 would be somewhere here. Of course, the energy of 2 pi would be exactly in the same place because that's the same. What about the energy of pi? Turns out it's lower. Not much, but lower. And you can connect these 2 plots, these points, getting something like that. The difference I'm not sure. Probably it's around 2.5 kcal per mole. And again, it doesn't tell you much. But from this, what I draw as so far, it's correct to say that the structure A is lower in energy than B. So A is the correct answer. But, now comes the but. A is a correct answer at 0 Kelvin, at the temperature when there are no vibrations. But when the temperature goes up, temperature, as you will probably learn in the next temperature more or less can be found that it's proportional to the speed of every atom or a molecule. Average speed, this means average. So if you have many molecules, then you can average the speed of every atom or a molecule, and then you can make a square, and you get that the temperature is proportional to the kinetic energy of these molecules. In fact, it should be momentum here, but let's write mv. Good. So, what does it mean? If the temperature is 0, it means that the average speed of molecules is 0. It means nothing is happening. But when the temperature goes up, molecules start moving. So they are moving in all possible directions. They are translating, they are rotating, they are also vibrating. Turns out that for translation you need very small temperature, maybe few Kelvin. It's enough for translation. To rotation, to start, the molecule starts rotating around probably a few dozens of Kelvin, 20, 30 Kelvin starts rotating. And the molecule starts vibrations around 100 Kelvin. This vibration, rotation of these two CH3 groups, is very low energy vibration. It means a low temperature is required for this vibration. So even in low temperature, it's like that. If you go with temperature even higher, it starts rotating freely. It means when the temperature is small, all the molecules are here. Temperature equals 0. But when the temperature is growing, the average speed of the molecule is something like that. Then the molecule can do the large movements like that. When the temperature goes even higher, we are with energy, total kinetic energy, here. This map is showing only potential energy. I'm speaking about total energy, which is kinetic plus potential. So when the temperature is higher, let's say T equal 270, we are much above this potential energy. It means that the molecule is freely rotating. Maybe because of it feels the lower energy, maybe sometimes it's rotating faster, sometimes slower, but it's rotating all the time. So if somebody answered A, it means it's a correct answer at temperature 0. If somebody answered both of them are correct, this is the correct answer at the room temperature. If somebody answered B, this is 49% correct answer, because in the room temperature, when the molecule is rotating, at 49% of the time it stays in the form B. So, as you see, sometimes it's very difficult to answer with only one answer correctly, like in this case. Okay, let's do another example. And this can be BF3 molecule, for example. And as you know, BF3, if you plot it, that would look something like that. There are no lone pairs here, there are lone pairs here. So if you want to plot it, you see that these three bonds would be farthest from each other if the molecule is planar. Now the bond is 120. When you start to folding the molecule like that, then the bond will get smaller, the angle will get smaller. Finally, when you fold it totally like that, the angle will become 0. You see it. So the best arrangement is flat. Now, so how the molecules look like according to the SEP theory? we have the fluorine atom, and the fluorine atom has 3 lone pairs. So the lone pairs will look like that. Flat, flat, fluorine, fluorine. Now again, there is a question. What about the lone pair? Can they rotate? That's a good question. The answer is no. And the reason is that this lone pair, and this lone pair make a linear combination. With the plus, 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 minus, minus, and well, there are 2 other linear combinations. And finally, no rotation is needed because the linear combination makes this lone pair look symmetric, spherical kind of. So there is no rotation needed to make the structure. And another thing is, anyway, we couldn't observe such a rotation. So it's a question that has no answer, experimentally at least. Good. The FSEP has one more rule. Rule number 4. Lone pairs repel each other stronger than bonds. This is an interesting rule because it says that when you have a molecule that looks like that, and now 2 of these positions, for example this one and this one, are taken by lone pairs, and the 2 other positions, for example this position and this position, are taken by bonds, it says that the angle alpha and the angle beta are not equal. It says that the lone pairs repel each other stronger. It means these 2 wants to be farther from each other than these 2. It means that in fact that it's not this sign, but it's this sign. But you can tell me, true, but these are not the only bonds in this, not the only angles in this molecule. You can also think about this angle that I'll call gamma, and by symmetry you can think about this angle that is also gamma. You can think about this angle that is also gamma, and you can think about that angle that is also gamma. There are 6 angles there. So what this rule really says is beta is larger than gamma is larger than alpha. So lone pair repel most. Lone pair and bond less, and bond less. Now, how big is the difference? Not big. Usually beta minus alpha (5 to 10 degrees). Let's try to predict some complicated molecules. By the way, I think it's a good moment to stop also and to ask another question. Let's take another molecule. No lone pairs. It means that the structure around carbon atom has 3 bonds, no lone pairs. 3 bonds, no lone pairs. Aha. If 3 bonds, no lone pairs, the structure is flat with 120 degrees. That's how it looks like. It's in the plane. Now, what about the angles? Should be 120. That's one way of looking at things. Another way of looking at things is telling that this angle is alpha, and these 2 angles are identical, called beta. Alpha is equal to, if I remember correctly, the experimental data show 118.2, which shows that this is not bad. Which gives for this one something like 120.9. But the most important information is that you knew that they shouldn't be equal, because there is no special reason why they should be equal. We only said that bond and bond repel weaker than electron pair and electron pair. But here we have different bonds. So you can expect larger repulsion. But good. We have the first part of the story. We know more or less what are the bonds. Second part is, I said the structure is flat, but you can imagine possibly a structure that looks like that. So one of the group is flat, one of them is like that. Well, why not? Now, I didn't write it, yes?
Right, because in this case, the orbitals didn't
Overlap.
overlap enough, and it isn't right.
True. So we are suggesting that here we have double bond because on each of the carbon we have a pi orbital like that from 2p. And here one of them would be like that and one of them would be like that. And you see this is 90 degrees. They cannot overlap. So there is a suggestion that this one has 1 bond less than this one. So it means it's higher in energy, right? So if we make a plot, energy plot again, we can call it structure A, and this one structure B. We say that this one is lower in energy, and this one is higher in energy. This one is again becoming the same, and again higher and the same. So we get a plot, something like this. Next test. For the other molecule, for the C2H6, we found that the energy of the B structure minus the energy of the A structure was equal to 2.5 kcal per mole. And we said in the room temperature it's really free rotation. Now we have a suggestion that if this structure would be correct, it means that the double bond is broken. And the energy should be much higher. That was Nina's argument. Now I'm asking you, what is the value of the energy here? Start from this side. 100. 200. 300. So we have 100, 200, 300, so far we don't know. 500. 200. 500, 200, 50. 50 to 302. Did I write everything? 50? Did I miss somebody's answer? No? 80, 100, 100. Good. Well, the experimental value, if I remember correctly, is 65. So it's around 30 times larger, maybe 25 times larger than this. And it's not as big as many of you expected. Does it mean there is a temperature when this can rotate? How big must be the temperature? You say there is no temperature. Why? You don't know. Well, the answer is that probably around the temperature 3000 Kelvin, this pi bond would be completely broken and we will have perfect rotation. But the question is, if the temperature 3000, this molecule is still stable, if it doesn't destroy into atoms. That's another question that I don't know to answer. Okay, I think it's good time to make a break. What time is it? Since human memory is not a very good one, I was trying to check the numbers I was giving to you, and I found some of them, but some of them not. So as we said, for C2H6, the rotational barrier was 2.9 kcal per mole. I didn't find the data for C2H4, but I have only the computed data. So the computed data is around 68 kcal per mole. I believe the experiment shouldn't be similar, but maybe +5, -5, I don't know. But now, are these numbers large? To answer these, I give you a molecule, and you know, fluorine is very active. It can react with many things. So the bond is not a very strong one. But now the question is, what is the energy of dissociating on two atoms? So that would be radical dissociation. You are remembering these things, right? This is 2.9, this is 68. Now we are dissociating molecule to two atoms. So it looks like most people support the 50. I mean, personally, I don't know what it is, but I checked. And the textbook I said says 39. So you have very good chemical sense. You can make a career, I guess. And this is one of the weakest bonds. Relatively small. Now, you see that the pi bond in this molecule is almost twice as strong as a sigma bond in this molecule, which is also an interesting issue. Okay, I give you some more examples, strange examples, I promise. One of them, oxygen atom, lone pair, hydrogen, hydrogen. You can change it to if I ask you what energy it requires, somebody tells me 0. You just rotate. And it's true. But if I want to change it differently, if I want to take the HH bond and do this, how much energy it requires? No, I always start from here, this time. 30. Okay, discuss some more. 50, 30, 50. 49. 50. 49. Okay. 50. 25. I ask you? Yes, I ask you, sorry. 25. 25, 30. 25, 30. 50. 50, 50. 10. 25, 25, and 10. 10. 70. Okay. Okay, again, I don't know, but I checked. And this requires 31. 2% were right. Who? Nice, nice. Good. Good sense. I didn't know. I guess 70. Probably my guess is, but I will be wrong. Good. Why I'm telling you these numbers? I give you the feeling how strong is the structure, how much energy you have to put to destroy it. Not to break the bond, but sometimes to break the bond, but just to change the shape. And another thing is that in some molecules, the energy is very small. In these molecules, the temperature is destroying the shape. But in other molecules, like here, here, or here, the temperature cannot destroy the molecule. Okay, the last example, maybe strange example, but I like it very much. This is called umbrella vibration. And the reason? Because when there is a strong wind, the umbrella becomes sometimes like that. And that's exactly this shape of this mold. So the umbrella mold. Now, what is the energy requires? You see that come from here to here, it means make these things first flat and then bend to the other side. What is the energy requires to make it flat? And the correct answer is 6. This is the reason why this molecule, I think we are discussing this molecule before, for a moment when I told you how people know. If you plot the energy for this molecule, and here would be the angle. I define the angle once again. Angle alpha here. You see when it is 0, all hydrogen are in the same place. The energy will be huge. When it is 180, all hydrogen will be in the same place, so the energy will be huge. So we see that for pi and for 0, the energy goes something like this. What happens between? We said that when it's flat, there is 6 kcal larger than when it's not flat. So the potential map looks something like this. Now we also said that every potential energy curve cannot be realized at the minimum. There must be some 0 vibrational level. So each of the well has their 0 vibrational levels and the first vibrational levels. And then turns out that the second one is almost the same in both. And then you have common one for both of them. And turns out that this vibrational level and this vibrational level, they can interact with each other. So finally, instead of observing one of them, you are observing 2 very close lines. And similar thing happens for the next one. Instead of observing one level, there are 2 very close lines. And because of these 2 very close lines, people know what is the energy required to do this. Because the splitting is somehow proportional to this one. Okay? Good. The end of strange topics. We come back to the main course of the class. And what we learn now would be... yes. So you see, the Lewis theory, very simple, just make 8 dots. Sepp theory, a bit more difficult, you have to remember all the possible shapes. And the valence bond theory, even more difficult because that's the linear combination of functions and you have to remember how the shapes of the orbitals look like and what is the energy of this valence bond theory. Now, probably this one is the most correct, less correct, and almost no correct. But now, do you think that this one is correct? Well, the question says probably the answer is no. So that's not really a question. But my point is that many people think it's correct, and if something is calculated within theory, it must be true. But the answer is no. This is not true. There are many others. More and more complicated coming that we are not going to learn. If you are chemistry major one day, there is a chance you will learn. That's what I'm teaching in the next class, in the quantum chemistry class. But another part is that this region is developing. It means this is not finished research. people are still working to make the theories better and better, and every year maybe 100, 200 new papers are written on the new ways of calculating these things and new way of interpreting these things. So I guess in 20 years the textbook may look very differently, and you can learn next few steps when the topics will be closed. Good. For today, I think valence bond theory is complicated enough and explains enough things that we can stop our teaching at this moment. Okay, with the valence bond theory, we said that just to remind you, if you have an s orbital and an s orbital, we said that they are making sigma orbital and the sigma antibonding orbital. And the sigma is lower in energy, sigma antibonding is higher in energy. We said when we have 3p orbitals and 3p orbitals, these are making sigma orbital, 2 pi orbitals, 2 pi antibonding orbitals, and the sigma antibonding orbitals. But now, this is the general rule. When you come to calculating these things and really obtaining the energy of this one, this one, and this one, and this one, you get a bit different picture. And what picture you exactly get, I will show in other textbook. This is Atkins, the same author like your textbook, but physical chemistry. It's not general chemistry book. And then one of the pages gives the plot of energies of the orbitals for the lithium dimer, beryllium dimer, boron dimer, carbon, nitrogen, oxygen, and fluorine. I will plot it in a moment on the blackboard, but I just wanted to show you. The first thing you see is that the pi bond's energy is almost not changing. The antibonding pi is almost non-changing. Here it's going a bit down. But the sigma bonding is really going down. And antibonding is kind of going down. And there is a moment, there is a place when the sigma and pi change place. Okay? So let's write this on the blackboard. If you take lithium dimer, one lithium atom has one s orbitals, but this is so low that we are going to forget it has 2s orbital, and other one has 2s, and it has 2p orbitals, 2p and 2p. Now lithium has only one electron here and one electron here. So it's going to make sigma bond and sigma antibonding bond. Now these p bonds, they are going to make this picture, but they are not occupied, they are empty. And in this situation, these two go lower than sigma. So the situation is similar, but it looks like that. Again, the same linear combinations, but just the energy of the linear combination is a bit different. And of course, the molecule looks like that. This was lithium dimer, of course. If you go to the next one, if you go to beryllium dimer, beryllium has 2 electrons here and 2 electrons here. So if you put them here, it will look like that. Then somebody tells me, okay, but this is maybe bad because the energy that you are getting from 2 binding orbitals is cancelled by the energy from 2 anti-binding orbitals. So the molecule shouldn't be stable. And more or less it's true. Well, The first thing is that this one is a bit lower than this one. So the total energy is a bit lower than two separated atoms, but not very much. So probably the beryllium dimer wouldn't be very stable. So that's way of thinking. If you go further, there would be the B2, yes, with a single electron, here and here. If the single electron comes to this picture, it enters the pi orbitals, making similar situation like we had for the oxygen. If you go further, with carbon, you have two electrons on each of them in the pi. Then, of course, they come here, making a closed shell molecule. You can go further, which is showing that carbon 2 have single bond, because this one is occupied, this one is unoccupied, and single bond, this one occupied and this one unoccupied. But the interesting case is that carbon dimer has double pi bond, no sigma bond. And you can expect that these molecules would be weak, and that's true, it's rather weak. It's an interesting molecule without sigma bonds. Okay, if you go further, it would be N2, and N2 has 3 electrons on the pi orbitals in the atom case, and of course that makes the triple bond here. Then you can go to oxygen, and in the oxygen there is a first change, and the first change is that these two levels are switched. So they come back to the normal picture that we know. Again, sigma is lower and pi is higher. And we know that, in fact, there are 4 electrons on the p orbitals, and they come like that, plus, minus, and single one come here. If you go further, there will be the fluorine atom. And of course, the fluorine atom looks more or less like that. So the only thing you have to remember that this picture is correct for oxygen 2 and for fluorine 2. If you want to make similar picture for the other dimers, that would look like that. That would be good for B2, what else? C2, N2. Good. Now finally we are coming to the problem that we had a few classes ago. There is a double bond in CO or a triple bond. All my life I was thinking that there is a double bond in CO. And Nina a few weeks ago said that there is a triple bond. And from that time I keep been thinking, is she correct or was I correct? And from all arguments I found, looks like she's correct. There is a triple bond, so I was wrong. I'm sorry to teach you wrong, and I try to give you all the arguments that I found that there is rather a triple bond in CO than a double bond. Okay? Let's start The first argument, you know, the CO energy of the CO bond is very large, the largest of all possible we have in your book. So that's suggesting a triple bond, not a double bond. Next one, the bond distance. Okay. I search through different molecules the experimental data for the single bond CO. And I write you the molecules I was searching. The first, okay, there would be quite a number of them. So CH3 O CH3, so-called ether. Okay, maybe I first write the molecules and then I will tell you what is the next one is C H H H H O H O H. Next one is C O O H. Next one is CH3 O H. Next one is and the next one is no, I don't like it, I'm using it, sorry. Should be, of course, aromatic ring. Okay, by the way, can you recognize these molecules? Some of them maybe you should know. This one? You know, right? It's used in the hospitals. Well, it was used in the hospitals. Now it's used something else. But 100 years ago it was used in hospitals to put people asleep. This one, I guess in Taiwan it's not very much used, but I guess in Ukraine you use it a lot. Yes, it's glycol, which is used in winter to add to the water in the cooler of the car, that it doesn't freeze. This makes the temperature much lower. This one, it's called formic acid. And why formic? Form in Latin means, well, I'm not very good to draw. Yes. The ants smell. When they bite you, it hurts a lot because they put this acid inside you. It's a formic acid. This, it's called acetic acid. It's vinegar. How do you say vinegar in Chinese? So, you know it. This one? Yeah, furan, but I guess it's used in the organic chemistry as a solvent, many other things. And this one? It's called phenol. And why should you know it? Because if you go to the toilet, it smells a bit. But when somebody cleans, there's other smell, a very chemical smell. That's a phenol smell. It's killing bacteria a lot. At least it was used 50 years ago. I don't know if they are still using or not, but smell is the same. Okay, now the bond distance. CH, in the phenol, it's 1364. Acetic acid, 1361. Furan, 1362. In formic acid, 1343. In here 1.411. In here 1.420. All of them? Yes. Okay, with the blue one I put the single bond. Now let's check the double bond. So the double bond in this one I have would be here 1.202. And this one I didn't check. I write a few other molecules that have double bond, and one of them would be CH3COCH3. Another one would be HCOH. Another one O. Another one O. Another one okay, maybe enough. Should you know these molecules? This one. It's called acetone. But why should you know it? Especially girls. Because it's the nail polish remover. Okay, that's a very strong smell. This one. Yeah, it's called formaldehyde. Why should you know it? That's a strange question, I know. After you learn the answer, probably you think it's a strange question. When somebody dies, you put the died person inside this. There's a smell of this. Strange, sweet. Especially when you want to become a doctor, medical doctor, you have to get used to this smell very well. This one probably you don't know, and this one you probably don't know. Let's just write down the bond. 1.215, 1.205, 1.191, 1.202, 1.225. Okay, what about CO? The bond in CO is 1.128. You see that these one are from 35 to 40. This one is around 120. This is much shorter. So this is suggesting that this is different type of bond than in these types of molecules. So I think it's a good thinking that it also corresponds to a triple bond. And finally, the molecular orbital picture. Good, thank you very much. So as you see, you have 6 valence electrons. When you put them, they're all on the bonding orbitals. So you have 3 bonding orbitals occupied and 3 anti-bonding orbitals unoccupied. Gives you the bond ordered 3. That Nina calculated that 6 bonding electrons minus 0 anti-bonding electrons divided by 2 gives you 3. So all of this way of thinking shows that there is a triple bond rather than double bond in CO. For me, there is another reason why I think that there is a triple bond now. Namely, if I take nitrogen, probably everybody of you would agree that nitrogen has triple bond, because that's what they are teaching in schools. Right? So now, one of the nitrogen has 7 electrons, and the other one has also 7 electrons. Together, they have 14 electrons. If I plot CO without putting the number of bond, one of them has 6 electrons, the other one has 8 electrons. They together give you 14 electrons. So these both structures have the same number of electrons. Such structures are called isoelectronic structures. And isoelectronic structures have very similar diagrams, like in this case. Try to think about that. What is the difference between this and this from the point of view of the atoms? The only difference is that the charge here is 7 and 7, here is 6 and 8 on the nucleus. That's the only charge. For the electrons, they should be exactly the same. Maybe a bit more attracted toward oxygen. So here the cloud would be perfectly symmetric. And here they would be larger around oxygen because it's more electronegative than. Maybe that's the only difference between these molecules. But this diagram should be very similar. So I think we can finish this topic saying that there is a triple bond in CO. Sorry for touching you before it's double. Good. Let's go further. How much time we have to the end? Who knows? Okay, maybe in other words, who had it in your hand ever? Hand up. Okay, this one is CaCO3. I have it in my hand. If I ask you who had it in your hand, everybody would raise the hand. Now I'm asking, if you had ever in your life this in your hand, hand up. 1, 2, 3, 4, 5. Why? You had your hand up. Why? What is it? Stone. Boo. If you are a woman, I agree, maybe you are right. Some women have this stone here. But you had it in your hand because this is sand. If you go to the beach, there is yellow sand everywhere. That's SeO2. That's IeO2. Okay. Now, NaCl. If somebody had it in your hand, I guess that's easy. Okay. Both of them are crystals. Okay. Now, one of them is ionic crystal, and it's this. And one of them is covalent crystal, and it's this. In this case, it means that every second atom has plus-minus charge. In this case, it means that between every two atoms there is a bond, chemical bond. My question is, how do we know from experiment that this one is ionic and this one is covalent? Which experiment can tell us that this is ionic crystal and this one is covalent crystal? Think for a moment. If somebody knows, hand up. Yes? Yeah, sure. We are guessing.
Maybe we can try to
Dissolve.
maybe.
Dissolve in a polar solvent. Okay. So that's one way of thinking. Oh, Nina says, if you take polar solvent, and for example, polar solvent would be H2O, because H2O has a dipole moment. So it's a polar solvent. Nina says, because this is a polar solvent, it has plus direction and a minus direction. It can interact with the positive ions and negative ions, taking them away from the crystal. Yeah, this is one way of the thinking. But now, you can take, for example, BaSO4. Okay? This one is also ionic crystal. But the problem with this one is it doesn't dissolve in water. It doesn't dissolve in anything. The energy of binding is so strong that it doesn't dissolve. So our experiment fails. Try to think about other experiment. Oh, good. This is much better because for any crystal you can find melting point. And then instead of using a solvent, the crystal itself becomes a solvent. Okay? So finally, if we are able to make a liquid out of this by melting and a liquid out of this by melting, we can try the following. We can put it in the box and melt, and then put here electrode with the plus and electrode with the minus charge. If the electricity is going through them, then we have ionic one. If there is no electricity going between them, then we have covalent type of bonds. In one case, the ions would travel to the other, so you have Na plus, Cl minus. So the Cl minus would travel to one of the electrode and this one will go to the other electrode. So this is one way of checking. After melting, they are ions. Now the last thing for today. On Friday, there are a few things happening. First, we finish chapter 3. Because we finish chapter 3, we finish everything what you need for the midterm. And on Friday there will be some time that you ask me questions. So try to read chapter 2, chapter 1 and chapter 3. And if there is something you don't understand, I can explain once again. So that's the first thing. Second, there are two more topics to discuss. One is metals and band structures. And one more topic is polar bonds versus polar molecules. Yeah. There is one more thing. We also learn the word like homo, lumo, that maybe you know from the high school already. So these are the end of the class for today. Thank you.